Good morning, everyone. First of all, thank you very much for providing me an opportunity to present my research work in this conference. My name is Muhammad Hamda Tariq, and today I'm going to present our research title Machine Learning Operation Optimization of Electrolyte-Based hydrogen production using a physics-informed digital twin for UK industrial cluster. This research focuses on improving the performance of hydrogen production system, particularly electrolyzer, by using advanced technologies such as machine learning and digital twin models. The motivation behind this work comes from the increasing importance of hydrogen as a clean energy carrier. In the UK, hydrogen is expected to play a key role in decarbonizing industries such as steel manufacturing, chemical production, and heavy transport. However, current hydrogen production systems are not fully optimized, and especially when integrated with renewable energy sources. Therefore, this study aims to develop an intelligence and adaptive optimization framework that improve efficiency, reduce energy consumptions, and enhance system reliability. Hydrogen is widely recognized as clean and flexible energy sources that can help reduce carbon emission in industrial sector in the UK. Achieving the net zero target by 2050 requires significant adoption of green hydrogen, which is produced using renewable energy sources. And one of the most promising technology for hydrogen production is water electrolysis, particularly using PEM electrolysis. However, despite its potential, this technology faces several operational challenges. First, the electrolyzers often operate at suboptimal efficiency, leading to higher energy consumption. Secondly, their performance can be unstable due to fluctuations in renewable energy supply, such as wind and solar variability. Thirdly, maintaining reliability and minimizing downtime remains a challenge, especially in industrial scale applications. So these issues make it difficult to scale hydrogen production efficiently and economically. Therefore, there is a need for smarter and more adaptive optimization approach. So hydrogen production through electrolysis has become increasingly important in the transition toward low carbon emission. So electrolysis uses electricity to split water into hydrogen and oxygen to produce clean hydrogen fuel without carbon emission, as shown in the diagram. So, when powered by renewable energy sources such as wind or solar, the resulting hydrogen is referred to a green hydrogen. This makes it sustainable energy carrier that supports the decarbonization of, of hard-to-abate sectors, including steel manufacturing, chemical production, and heavy transport. As the UK work toward its net zero 2050 target, green hydrogen is expected to play a key role in reducing dependence on fossil fuels while supporting industrial growth and energy security. However, to make hydrogen production economically variable at scale, it's essential to improve the efficiency and operation performance of electrolyzer system, which is the focus of this research. So the problem, traditional optimization method used in electrolysis system are mostly based on fixed control strategies. These methods rely on predefined parameters and simplified models that do not account for real-time variation in operation conditions. For example, change in renewable energy supply or system load are not dynamically handled. As a result, these systems cannot respond effectively to fluctuations, leading to inefficiencies and energy losses. Additionally, conventional methods lack predictive capabilities. They cannot anticipates system failure or performance degradation, which increase maintenance cost and downtime. Overall, these limitations highlight the need for intelligent systems that can learn from data, adapt to changing conditions, and optimize performance continuously. This is where machine learning and digital twin technologies can provide significant advantages. The main objective of this research is to develop an advanced optimization framework for electrolysis-based hydrogen production. Specifically, this study aimed to integrate machine learning with the physics-informed digital twin to improve system performance. And the key goals are reducing reducing energy consumption during hydrogen production and increasing operational efficiency and minimizing system downtime through predictive maintenance. Another important objective is to enable real-time adaptive optimization, meaning the system can adjust operational based on changing conditions. This is particularly important when working with the renewable energy sources, which are the inherently variable. Ultimately, the proposed framework aimed to support sustainable hydrogen production and contribute to UK industrial decarbonisation eff- effort. So, the methodology of research combined both data-driven and physics-based approach. The framework consists of four main stages. The first stage is data collected from electrolyzer system using sensors that monitor the operational parameter. Second is the data collected is processed and prepared through cleaning, normalization, and feature engineering. And the third step is machine learning model are developed and trained to predict system performance metrics such as hydrogen production rate and energy consumption. And the final step is a digital twin is created to simulate the physical system and enable real-time optimization. By integrating these components, the system can continuously monitor, predict, and optimize its performance. So this approach allows for dynamic intelligence control, which are not possible with traditional methods. So this study focused on a proton exchange membrane or PEM electrolysis system. This type of electrolysis is particularly suitable for integration with renewable energy due to its fast response to changing power input. The system is equipped with sensors that collect important operational data. These are include temperature, pressure, voltage, current density, hydrogen production rate, and energy consumption. So these parameters are critical for the understanding system performance and effective efficiency. In this research, a data set simulated operation condition was used, representing different real-world scenarios. This data forms a foundation of training the machine learning model and developing optimizing optimization framework. So the machine learning integration plays a central role in this research by enable predictive and adaptive optimization. In this study, su- supervised learning technique, particularly artificial natural artificial neural network, are used. These models are trained using historical operational data to learn the relationship between input parameters and the system performance. The input include variables such as temperature, pressure, and current density, while the output includes hydrogen production rate and energy consumption. Once trained, the model can predict system behavior under different operation conditions, and this allows the system to identify optimal parameters, setting the maximum efficiency and minimize energy use. Additionally, machine learning enables predictive maintenance by identifying patterns that indicate potential system failure before it actually happened. The digital twin is virtual representation of the physical electrolyzer system. It combines physics-based model with real-time sensor data to simulate system behavior accurately. The digital twin allows us to monitor the system continuously and evaluate its performance under different conditions. One of its key advantages is the ability to set different scenarios without affecting the real system. For example, we can simulate changing in energy input or operational parameters and observe their impact on performance. So this enables real-time optimization and better decision making. The integration of digital twin with machine learning further enhance its predictive and adaptive capabilities. So this machine learning digital framework for flow, the proposed framework integrate a machine learning and digital twin into a unified system. Machine learning model predicts system performance based on input parameters, and these predictions are used by the digital twin to simulate and validate system behavior. The digital twin provides feedback which is used to refine the machine learning models and optimize system operation. So this creates a continuous feedback loop that improve accuracy and efficiency over time. As a result, the system can adapt dynamically to changing condition and maintaining optimal performance. And the system architecture consists of four main layers. The first, data acquisition layer, collect real-time sensor data from the electrolyzer system. Second layer, the data process layer prepares the data from analysis through cleaning and feature extraction. The third layer, the machine learning layer, analyze the data and predict system performance. Finally, the digital twin layers simulate the system and enable real-time optimization. These layers work together to create an intelligence and adaptive system that continues improve performance. The result of this study shows significant improvement as compared to operation system. Energy consumption is reduced by approximately 15 to 20%. System downtime is reduced by 25 to 35% due to predictive maintenance, and operational efficiency increase from around 65% to 75% and 78%. These improved demonstrate effectiveness of proposed machine learning and digital twin framework. The results are based on simulation experiment comparing the optimized system with the baseline system. Comparison with conventional system. When compared to traditional system, the proposed framework show clear advantages. Conventional system rely on fixed control strategies and cannot adapt to changing conditions. In contrast, the machine learning digital twin framework provides dynamic and real-time optimization. This lead to a better efficiency, reduce costs, improve system reliability. Additionally, the ability to predict and prevent failure enhance overall system performance. In conclusion, the research demonstrate the potential of integrating machine learning and digital twin technologies for optimizing hydrogen production. So the proposed framework improve efficiency, reduce energy consumption, and enhance its reliability. It is it also supports the UK transition to a low carbon energy economy by enabling more sustainable hydrogen production. Overall, the approach represents a significant step forward in intelligence energy system optimization. For future